All right, when last we met, we talked about things like that. Is that screen flickering?
Yes, it is.
Wow.
And that's gonna.
Is that going to be annoying?
Can they give us a new bulb for this thing?
Well, I don't know if that's going to solve the flickering. Let me give him a call. Somebody will come. All right, well, we looked at these types of problems where we determined if things were aromatic or not aromatic or anti-aromatic. And then we used those distinctions to figure out what would be the most likely product in a given reaction or a given process, or which is a stronger base or a stronger acid or more nucleophilic or whatever. So all of those things will come in. Please continue to review that. Let's have a quiz on, can we say Wednesday? On this stuff? Okay, so 2 days. No, just let's do it Monday so we can do it on this whole chapter. Let's do it Monday. Okay. And we'll do it on the whole chapter. So today we're going to finish up talking about these kind of stability effects of benzene and then get into the reactions on the benzene molecule, which is actually chapter 19. So the last part of this is reactions at the benzylic position. Where's the benzylic position? Close. I think you were closer. The first carbon away from the benzene. Yeah. So here's your benzene ring. So you have some chain coming off of it. The benzylic position is that first carbon away from the benzene ring. Why is that important? Right, because that's the only position here that's accessible by resonance to the benzene ring. So something we talked about last semester was that things like these types of cations or these types of radicals are particularly stable because they can be resonance stabilized by the benzene ring. So that's something you've already sort of looked for when we talked about substitution, elimination, and all that, and the radical processes, that that one position right away from the benzene ring has this special stability. But there are actually some other reactions that can do this as well. For instance, that position is particularly susceptible to oxidation. If you take a molecule like this and oxidize it with either chromic acid type conditions, which we talked about before, or potassium permanganate, another highly oxidative condition, you can sort of cut that whole chain off and make benzoic acid. This is the primary way to make benzoic acids. It's not very useful in other types of long-term syntheses because obviously you cut everything off. But this is commonly used to take things like toluene, those types of molecules, and turn them into benzoic acids or diacids or triacids or whatever. pKa of benzoic acid is about, oh, I should know this.
You haven't memorized the whole chart.
I haven't memorized the whole chart, apparently. I thought I knew this. No, it's on the order of like 3 or 4. Yeah. So that can be useful. And the interesting thing to remember here is this actually can't be done in other ways. So like benzene itself is not susceptible to oxidation of either condition, nor is a long alkyl chain. But when it's an alkyl chain on a benzene ring, you have that special benzoic position that can be oxidized. We've also, some stuff that we've talked about, well, we haven't, but hopefully you have in a previous class, is free radical bromination. You can selectively brominate to the benzoic position also. Same way you could do it to an allylic position. Whoops, actually, you can activate this with any kind of radical initiator, but let's be consistent with the book. And that's heated up. Oh, sorry, one more thing we should mention here. You need, as usual, you need these hydrogens to be able to oxidize this. So something like, as with the alcohol oxidations, something like this you won't get any reaction because you don't have those hydrogens. To do it. All right. Same thing with the free radical stuff. You can go back and take a look at those mechanisms if needed. And then just to review, we can also do very rapid SN1 and E1 type processes at the benzoic position. So I'm going to ask you now, just as practice, if we start with this kind of benzoic halide, this is fast. It will rapidly fall off to form a carbocation. And now, as a little bit of review, see if you can draw the 3 other resonance structures of this carbocation. Okay, hopefully you got this one. This one. And this one. Yeah? Okay. So that's the resonance that shows the stability of this carbocation, which means that we can do these types of reactions. So when something like this is reacted with water, it will likely substitute making these things somewhat water sensitive. You have to be aware of these kinds of structures, because we usually think, I think we made the kind of assertion last semester that SN1, E1 processes are fairly slow because of the carbocation that they form. But in fact, that's not true. They can be very rapid and very favored when you have things like benzylic cations that are very stable. So you can do these types of reactions. You can also do, see if I can find some conditions here. You can do a very rapid dehydration E1 elimination with these types of structures. So this would be an SN1 process, this would be an E1 process. Those things are readily performed, readily prepared, and very rapid. Okay, so nothing too new there except for the oxidation, but you can indeed react with benzene side chains. Then the last reaction that we'll talk about in this chapter is reduction. Benzene can't be easily reduced with hydrogen as double bonds are. Okay, because of its special stability, it needs a little more power. So you can do this with very strong catalysts, high temperatures, and high pressures. If you have hydrogen with a nickel catalyst, and the conditions here are severe, 100 atmospheres, 150 degrees C. Right, so a pretty severe reaction, and then you can actually make a cyclohexane from a benzene. However, perhaps more importantly are the reductions that we've already learned, where you leave the benzene intact. So you can take something like a styrene and react that with palladium or platinum catalyst. Whoops, hydrogen also, of course. This is only at 2 atmospheres, so just a slightly pressurized container. And at room temperature, you can reduce the styrene part and leave the benzene intact in good yield. And then there's one reduction, a solution reduction. It's a type of dissolving metal reduction. Where have we seen a dissolving metal reduction before? Yeah. Right. In alkynes, alkynes can be reduced with dissolved sodium or lithium metal in ammonia, in liquid ammonia, right, to make a trans-alkene. So similar conditions here, but with a benzene, you can react benzene with dissolved metal, and this is done in the presence of methanol, but the important thing is really just the metal, and again, liquid ammonia. And it's not a full reduction, but it's a reduction to 2 non-conjugated alkenes. And this is known as the Birch reduction. Can also be done with lithium. A variety of this is what's used to make meth. They use a Birch reduction using lithium from lithium batteries. The mechanism of this, you don't have to know it, but let's just quickly go through it because it's kind of interesting and it makes the next thing we're going to talk about make a little bit more sense, I think. It's a radical process, and if you saw the previous dissolving metal reduction mechanism, this might make some sense. So you have sodium with an extra electron. It's 1 valence electron. Okay. And that's going to combine with one of the electrons from this double bond. The other one's going to come here, and you're going to have a homolytic cleavage of this double bond as well. You put all that stuff together, what you ultimately get, and I'm going to draw in a couple of the hydrogens now too because they're going to be important. You get these two double bonds, you get a lone pair on this carbon, and a single radical on that carbon. If you follow those arrows around, you should see it. So now you have a lone pair here, so that carbon must be negatively charged. That's now a carbanion, offset by the positively charged sodium. And that's going to be a strong base that will deprotonate the methanol. Okay, so that's where the first hydrogen comes from in the reduction. Okay, we still have this radical down here. And then it's going to take another equivalent of sodium to give its electron over to this one. And you're basically doing the same thing again. You're forming a lone pair negative charge here, which is then deprotonating the methanol. All right. Now, why is that important to look at that methanol, or to look at that? Well, because of the regioselectivity, the mechanism I meant, because of the regioselectivity of this reaction. So if you have something like this, toluene or something, and you want to reduce it, there are two possible products, and they're not the same. You do that reduction, you can either make this one or this one. Right? That's just the two possible ways that you can draw the product, and they're actually two different products. Okay, so this is actually the product, and this is not observed. All right. So why is that? Well, it has to do with this mechanism. We're going to get into this more in the next chapter, but this is a good introduction to it. Depending on what this R is, it can either be electron donating or electron withdrawing. R is an alkyl group, is usually electron donating. So what we see is we have to look at the two possible intermediates here. So the intermediate that gets to the product is one that has an anion here or over here. Right? That's one of the intermediates. And the other intermediate for this one would actually have the lone pair here, because the lone pair is where the hydrogen ends up. So if this lone pair is stabilized by the R, you would get this product. If the lone pair is destabilized by the R, you get this product. And let's look at some examples of what that might be. So imagine, for instance, that the group on there is an OH. An OH is electron donating because it has lone pairs that can kind of go down like that, right? So a lone pair here with a negative charge would be very destabilized by that alcohol. And you would not expect to see this. So in this case, the lone pair is destabilized. So if there were an alcohol there, you would expect to get the other intermediate. If you had an alcohol here, now this one is, we'll just say it's okay. It's not affected by the alcohol. Okay, but something that can donate electrons like that. Also, alkyl groups fit in that category as well. That would be unlikely to form this intermediate or this product. Okay, and then you'd get the opposite if you have an electron withdrawing substituent like a ketone or an aldehyde or something like this. So let's say we have a molecule like this. Okay, and my question then, well, actually, let me draw this a little bit differently. And the question is, which product do you get if you do a Birch reduction? Are you going to get this one or this one? Now you look at the intermediate and you determine how that ketone plays a role in stabilizing that intermediate. So let's do the same thing we did before. Let's look at each intermediate that leads to these products. So the intermediate that leads to this product is this one. The intermediate that leads to this product is this one. So is one of those carbanions stabilized by the ketone? At least relative to the other? Why? Right. So this is in resonance. Where it's stabilized by resonance with the ketone. Whereas this one is not stabilized by that same type of resonance. So this would be the favorite product. So that kind of brings us in now to the next chapter, which actually is going to talk about how these types of things affect the chemistry of benzene rings in all types of different reactions. All right, so let's do that. Reactions of benzene. Now remember, just pull this up from the book here. Remember we talked about this before? That you could brominate alkenes, you can brominate conjugated alkenes, you can't brominate benzene. Yeah? Okay. Keep that in mind, because people seem to forget that when I grade tests sometimes. So you can't brominate benzene. What you can do is brominate benzene with help. If you react this with bromine in the presence of an iron catalyst, you can actually brominate quite nicely. But you've actually done something very different. This isn't an addition reaction, this is actually a substitution reaction. The bromine has substituted for what? A hydrogen. That also tells you that something different has gone on mechanistically, because hydrogen is certainly not what we think of as a leaving group with a substitution reaction. And in fact, that's the case. This is not nucleophilic substitution. This is electrophilic aromatic substitution. Electrophilic aromatic substitution. And instead of SN1 or SN2, it's SEAR. E for electrophilic, AR for aromatic. And let's look at this mechanism. So we're going to go through many mechanisms throughout this chapter of electrophilic substitution. They're all going to be the same, which is nice. So it's the same thing over and over again. The point is we have to make the electrophile much, much better. A bromine molecule is an electrophile. We know that. We can add it to a nucleophile like an alkene. But it's not a very good electrophile. What would be a way to make it a very good electrophile? What would be something that is a very good electrophile? Right, yeah. A cation would be way more electrophilic than that, because that's neutral. So that's essentially what all these various additives that we're going to talk about do, is give us a cation, give us a way to make this electrophile much stronger. What actually happens here is you take the iron tribromide, and the bromine attacks the iron, making this kind of a complex. And then ultimately forming an ionic compound, making Br+. One of the bromine atoms attacks the iron.
Then why do you have the next step where the bromine is attacking a bromine?
It's disconnecting.
Oh, I see what you're saying. Okay.
Okay, and then this thing here is now our electrophile. Now, I'm going to put quotes around it, because as with most things, it's not that simple. In fact, it's a complex that sort of acts like Br+, kind of like how we say a Grignard reagent acts like a C-, or a hydride reagent acts like an H-, but it's not actually what it is. We're going to pretend that this is a Br+, and that's actually what's doing the reaction. So the overall mechanism of the aromatic, or the electrophilic aromatic substitution looks like this. We're going to take the benzene. Okay. And we take our, we're actually going to use this middle complex here, because that more approximates what's real. And the benzene now is acting as a nucleophile, attacking that bromine, which we know is acting like Br+. And when that attacks, you end up with this intermediate, and this is kind of the crucial intermediate that we're going to be dealing a lot with. The bromine attaches on one side, which leaves the other side a carbocation. So this is basically the same mechanism as addition to an alkene. So now, in addition to an alkene, a nucleophile would attack that carbocation. But because of the special stability of benzene, we're actually going to want to reform benzene. So this is where it deviates from our previous reactions, is that some base, probably this leftover thing, or the solvent, I'm not going to specify it, I'm just going to say a base, instead of attacking over here, it deprotonates the hydrogen, doing kind of like the second step of an E2 reaction. And that reforms the benzene. And that's the big difference, that in other types of addition reactions, there's not a drive toward elimination, because there's no reason necessarily to reform the alkene. But in this case, reforming the alkene restores aromaticity, and we just talked about last chapter how that's so important from a stability standpoint. All right, so this is a key mechanism. Make sure you know this. We're going to be talking about it over and over again, doing it over and over again with different types of reagents. And there are other ways to do this as well. We're going to be seeing many more reactions that use the same type of mechanism, like this one. Okay. In this case, straight up chlorination with chlorine gas would not be electrophilic enough to do the reaction. But when we use this aluminum trichloride, or some books will use iron trichloride, some kind of metal trichloride, a strong Lewis acid, you can make that chlorine electrophilic enough to be attacked by the benzene and undergo the substitution reaction. So that's kind of the general thing. For iodine, you can do the same thing. But the molecule usually used is copper 2 iodide. And then you could go on from any of those and make Grignard reagents or do any of the other stuff that we've talked about. Yeah.
So why doesn't that keep happening? As far as like making like a chlorine, more increasing?
Okay. Yeah. Good question. We're going to get into it more, but let's talk about it now. What do you think is more nucleophilic? Because that's really what we're asking now. The benzene by itself, or benzene with a chlorine on it, and why? Anybody? What's more nucleophilic? Why?
Just for the benzene, would you be talking just as the resonance stabilization from the stability standpoint?
Well, but how does that affect nucleophilicity? Or does it? What else do you think? How does that chlorine affect it?
I guess I could add, like a, no, I don't know.
Benzene ring by itself is more liquid,
Why?
because of the no hydrogen on it. If we add chlorine to it, like that will.
Okay.
Just because the seal is electron withdrawn.
Yeah. Yeah, the chlorine's going to be a little bit electron withdrawing, right, because of electronegativity, inductive effect. That pulls some electron density out of the ring, makes the benzene a little bit less electronegative. So that's really the answer to your question, is when the halogen's on there, the benzene is a little bit less reactive than it was before. And we're going to see when we put other types of things on there, the opposite can happen. And you can actually make something that's now more reactive than benzene and therefore difficult to stop successive reactions from happening.
So the Cl makes it less reactive.
Less nucleophilic, yeah. Yeah. I was careful there because we're also going to talk about nucleophilic aromatic substitution, which is the opposite when you want the ring to be the electrophile. We'll get into that later. Okay, so let's look at some other common reactions of benzene. Let's number these and keep track. So let's say number 1 here is halogenation. Number 2, sulfonation. Benzene can react with sulfuric acid. To form a sulfonic acid. These are important for things like, if you remember, tosylates, mesolates. Those are all types of sulfonic acids. And the mechanism is very similar. So, in this case, H2SO4 actually kind of, hang on, let's be a little bit more specific here. This is concentrated fuming sulfuric acid. Okay. Not real nice stuff. But what fuming sulfuric acid does is it's breaking down into water and sulfur trioxide. And sulfur trioxide is actually very electrophilic. So you've got the benzene, attacking the SO3, whoops, that's minus. Fuming. Okay, and that type of a mechanism and then it's again deprotonated by base, usually the conjugate base of sulfuric acid here, to regain aromaticity. Remember, SO3 minus is actually a pretty stable thing because of the resonance. Remember, it looks like this. Draw one out just for fun. Okay. So then that can be protonated by sulfuric acid, by strong acid. Because that's by itself I mean, it's not a strong acid like sulfuric acid, but it's a relatively strong acid. Relatively low pK. And actually, the reason we were very specific about that fuming concentrated acid, something that will become important later, is the reverse reaction. If a sulfonic acid is reacted with dilute sulfuric acid, wait, that's not a sulfonic acid. Okay. It can actually be eliminated or be substituted for hydrogen. And we're going to use that later as we try to synthesize various specific benzenes. All right? Questions about that? All right. Now the reaction that we just did last week in lab, nitration. I think you probably know this one. You react a benzene with nitric acid and sulfuric acid, and you can make a nitrobenzene. I'm going to show you how you make the electrophile known as a nitronium ion, and then you can draw the substitution reaction as practice. So here's nitric acid. Right? HNO3. And then sulfuric acid can actually protonate the nitric acid. Okay. Whoops. Sorry. Wrong hydrogen. That's something electron in there. We have to make water because we need a leaving group here. And then that leaving group leaves, and you form an NO2 plus ion. And that's known as a nitronium ion. Okay, so that is your electrophile. See if you can draw the mechanism of this first reaction here. Using this as your electrophile, show benzene attacking that, draw the same mechanism that we've been talking about.
So the orange gets, or, no, which
One of those bonds moves up
Yeah.
the oxygen.
Wait, so this is not, what, this is from that?
No, that's- Oh, you got it.
Yeah. And then, so wait, this is, this minus is going to be, so come back down.
No.
So it should stay at 14 minus.
No, it's the nitrogen.
Oh, yeah. So there's going to be two double.
Okay, so hopefully you came up with something like this. Now, a lot of people had that the benzene attacks the nitrogen. However, remember, nitrogen can't have more than an octet. So you need to also allow those electrons to move back up to the oxygen. That's what NO2 looks like. It's neutral overall. You have the positive on the nitrogen, the negative on the oxygen. And then you've got your cation on the other side. So some base, probably the HSO4 minus or whatever, B for base, you can always use that. Deprotonates here, and you end up with your product. And that's the reaction that you did last week. Now, nitrobenzenes by themselves have various uses in various things. But the other utility of this, and I guess we'll call this 4, is that nitrobenzenes can be converted into anilines through reduction. And that's usually using a metal in the presence excuse me, of HCl. So a different type of metal reduction. We will talk about that, or we'll use this sometimes. That is 4, right? Yeah, this was 3. We'll use that sometimes because there's no good way to do electrophilic addition with an NH2 type electrophile. There aren't really NH2 type electrophiles. So you do it by making a nitrobenzene and then reducing it to the aniline. All right. So I think probably the last stuff we'll get to today is this Friedel-Crafts chemistry. The Friedel-Crafts alkylation is a way to put carbon stuff on benzene, but it actually has a lot of drawbacks, which we'll discuss. It looks like this. In its most basic form. You react it with an alkyl chloride in the presence of aluminum trichloride. It's a very old reaction in the 1800s. And they reported about 66% yield here. So not a great reaction. Here we're going to talk about how this works, and then we'll get into some of its drawbacks, some of which we've already discussed with the before. But okay, how this works is, again, you want to make something that's not particularly electrophilic into a good electrophile. So the alkyl chloride here, we know that can be electrophilic because you can do the nucleophilic substitution on it. But it's not electrophilic enough really to be attacked by benzene on its own. The aluminum comes in much the same way that we've seen before. So you've got this type of alkyl chloride, and then you've got the aluminum trichloride, which is a strong Lewis base, gets attacked by the halide. You form this sort of thing. Which makes this kind of complex. And then in this case, it actually does get more or less converted to a carbocation. And that's your electrophile for the reaction. So you can draw the exact same mechanism we've been doing with that electrophile to do the Friedel-Crafts alkylation. So here's the problem. Couple problems. Let's say you want a long chain. You want to alkylate with N-butyl instead of sec-butyl. Well, it doesn't actually work. You get some of it, but mostly you get the sec-butyl. So this is about 35% the thing you wanted, and 65% this thing that doesn't work. Why do you think that is? Yeah, right, carbocation shift. If you look back at this mechanism of forming the electrophile, if you do it with this one, you're going to form a primary carbocation, which we know is very unstable. So it quickly shifts to the secondary, forming this product. So this process is very susceptible to carbocation shifts, which means you have to be careful with it. So we'll call that problem A. Problem B, it only works for alkyl chlorides okay. So you can't use it with phenyl chlorides, vinyl chlorides, things like that. So that's not really a problem, that's more of a limitation. And then problem C, you can get multiple additions as we've described before. An alkyl benzene, like an ethyl benzene or a butyl benzene or whatever, is more reactive than benzene by itself. So there's a good chance that when you do your substitution, and this is part of the reason the yields were relatively low, you get what you want, but you also get things like this. And other various multiple addition products. So it's interesting how different books approach this problem. This book says you can have these polyalkylations, but the problem can be avoided by choosing conditions that favor monoalkylation. It doesn't really tell you what those are, but basically it's different amounts of dilution and temperature, doing it at lower temperatures. So in this, they say that for the remainder of this chapter, assume all Friedel-Crafts alkylations are performed under conditions that favor monoalkylation unless otherwise specified. Other books say that you just shouldn't rely on this and you should do this in a different way, which is the next part, the acylation. But we'll stick with this, with what this book says. So the final problem is that you can't have, and I'm going to be more general about this than the book is, you can't do this in the presence of electron withdrawing groups, things that are very withdrawing. The reason for that is that the benzene simply isn't reactive enough to react with the alkyl nucleophile or electrophile. So examples of strong withdrawing groups are things like nitro groups. Nitrobenzenes are not reactive toward Friedel-Crafts alkylations. And the book specifies it to just with nitro group. Well, what it says is there are certain groups, such as nitro group, that are incompatible. In fact, it's many electron withdrawing groups, from nitro groups to ketones to acids, stuff with double bond to oxygen. We'll get into that more when we talk about the directing abilities of these things on Wednesday. But that's it for today. Let's head upstairs and get started with NMR.
We just do NMR.